Mr. Halp coming at you again. This is the second lesson 1.1, Parent Functions and Transformations, Part 2. So here's a list of all the transformations that you can perform to those parent functions we talked about last class. So you can do a horizontal and vertical shift. In geometry, you would have called this a translation. You can reflect over a line, and that's the same term in geometry. It would have been called a reflection. Typically, in algebra, we reflect over either the x-axis or the y-axis. We can do a shrink or a stretch. In geometry, this would have been called a dilation. The other transformation that you can do is a rotation, but that's more of a geometry thing because it's very hard to do algebraically. So we just don't talk about this one. Let's take a look at an example of something that's going to do a stretch or a shrink. So we're going to graph each function and its parent function and then describe the transformation we see. So in this problem, we're looking at the function g of x equals 2 times the absolute value of x. So we're going to start by just creating a table of values. So let's see here. Here's my table of values. We'll do x here. This will be g of x, which is equal to 2 times the absolute value of x. And I'll just do some values for x. So -2, -1, 0, 1, 2. These are the x values I like to start with. But really, you can use whatever x values your little heart desires. We'll plug then that -2 into my equation. So let's see here. That'll be 2 absolute value of -2. Let's say the absolute value of -2 is 2. So this will end up being 2 times +2, which is 4. We're going to repeat that process with the others. So let's see here, for the next one, it'll be 2 times the absolute value of -1. Let's see here, that will give me 2. Then I'll have 2 times the absolute value of 0, which is equal to 0. I'll have 2 absolute value of 1, which is 2. And I'll have 2 absolute value of 2, which gives me 4. So now when I go over here and plot these points, I got -2, 4. -1, 2, 0, 0, 1, 2, and 2, 4. And you'll see there is my absolute value graph. And I should have recognized that because if I look right here, I see the absolute value function, which means my graph should look like a V. But what is that parent function? Let's put that parent function up there so that we can compare the two. So we're going to put that parent function up there right now. So that would be y equals the absolute value of x, just the absolute value by itself. And if you remember my table of values that I used for that y equals the absolute value of x, it was -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. And if you need to go back and watch the last video. That's where I explained where all those things came from. And if I plot those points, I'll put those up here. I'll end up with the absolute value graph. Now I'm using a dashed line to represent the absolute value graph, that parent function, just so you don't get that confused with the actual graph, which is 2 absolute value of x, which is right there in red. So what are the transformations I see? So I'm looking here, and again, that's y equals the absolute value of x, and then the other one, this guy right here, that's g of x, which is equal to 2 absolute value of x. And if you see that, what it looks like has been happened, it looks like I took the two ends and I kind of pushed them up this way, right? So what happens is this is called a vertical stretch. Now, you can simply say the V gets narrower. I'm totally okay with that. We'll work on the vocabulary a little bit more down the line. But this is technically what is called a vertical stretch because I'm pulling it that way. Let's take a look at another problem. So here we have 1/2 x squared. Okay, so let's go through here and let's create for me a table of values. So here's x, here's h of x. And again, I like my values, -2, -1, 0, 1, and 2. And then we'll just plug it into the equation. So I have 1/2 times, it'll be -2 squared. So order of operations says that I should do the exponent first. So -2 squared, that'll give me 4. So that's 1/2 times 4. And then I'll do 1/2 times 4, which gives me 2. So my first coordinate pair is -2, 2. Now go ahead and plot that. Let's go to the next one. 1/2, and it's -1 squared. So that's here. So that's 1/2. Negative 1 squared is positive 1, which gives me, let's see, so that's just 1/2. So my next coordinate pair is negative 1, 1/2. Okay, we'll do our best with that graph. And then I'll just go ahead and fill in the rest. I'm going to repeat the math, but there's no sense in me telling you what it is. So 0, 0, 1, 1/2, and 2, 2. Those will be the other 2 points that I'll end up with if I just did the math the same way I did the other one. I'll plot those points, and you'll see the U shape, right? The U shape starts popping up. Look, there it is. There's the U. If I connect the dots and I do it the right way, I end up with a U. Now, it's hard to tell how this compares to the parent function. So let's put the parent function on there. And that's y equals x squared, right? A quadratic. And we should see that because we see the x squared in the problem. So let's do that. Y equals x squared. So I'll do my good old table of values that I was using before. I'll fill in those numbers that I knew that I probably have memorized by this point, and I'll plot those points. All right, there we go. Perfect. So now what you'll see is that the red curve, which is my h of x function, versus the parent function, which is right here. That's y equals x squared. Okay. What you'll see is the red function looks wider than the green function. So what we have here is a vertical shrink. This is a vertical shrink, right? Because what happens is it actually looks like this was pushed down to make it look wider than what it is. It's that time again, folks. So I would like you to pause the video right now, and I'd like you to try these 3 problems. So go ahead and give it a try, and then we'll go over the answers here then shortly. So give the video a pause at this point. So we have g of x equals 3x for our first example problem, and I, as always, am going to make a table of values. So I got negative 2, 1, 0, 1, and 2. And my math's going to be 3 times negative 2, so that'll give me negative 6, negative 3, 0, 3, and 6. And I'll go over here and I'll plot my points. So I will get them plotted right here. And then let's see how good of a job I can do drawing a straight line. Hey, that's not too bad. So this line right here, the blue line, that's my g of x function equals 3x. And then if I put the parent function on there, which again, I'll refer to my table of values that I had before, but you'll see that it looks like this. So what happened? I think it's easy for us to say that the slope is steeper than the parent function, right? Because if I look at that, if I look at my blue line, the slope in there is definitely, it's much a steeper line than the red line, the parent function that I started with. All right, let's take a look at number 6. So this was 3/2 x squared. So what we'll do is we'll go ahead and we'll start here and we'll create my table of values. So again, we'll have x. I'm going to use those same values. Are you tired of me using the same values? I'm not. I like those. They're nice values. They're the ones that I'll start with. Typically, I can see things, and if I can't, I'll do more numbers if I need to. There's no harm in that. So let's say we'll do 3 over 2 times negative 2 squared. I do that math, bust out my calculator. I get 6. I'll get 1.5, 0, 1.5, and 6. So I'll go out here and I'll plot these points. So it's here. So negative 2, 6 is up here. I got negative 1, 1.5, 0, 0. I'll plot the other 2 points. Okay, and I will graph my line. Look there it is. Now the parent function, what about the parent function? Well, let me plot those points right there. We got those going on. Ooh, now this one's a little hard to see. Okay, but if we look at the parent function, right, which is the green line, right, that's y equals x squared. And we compare that to, again, my h of x, which is 3/2 x squared. You'll see that, again, we've pulled on that. This is definitely a vertical stretch. But we can say something like this. We can say h of x is, well, narrower than y equals x squared, or than my parent function, okay? I'm not looking for you to necessarily know that perfect vocabulary yet. So we're just describing what we see. That's all. Let's look at number 7. We're going to look at number 7. I have c of x is equal to 0.2 times the absolute value of x. Again, I'm going to use that table of values. I'm going to come up with this table of values to help me graph that. All right, so -2, -1, 0, 1, and 2. Let's see here. That's 0.4, 0.2, 0, 0.2, 0.4. Man, I don't know. Those numbers, when I try to plot them, that feels like that's going to be pretty tough to do. Because these decimals, right? We're not locked into this table of values. As a matter of fact, maybe I want to pick some smarter numbers. Maybe I want to pick some bigger numbers. Maybe I want to guess and check until I get something that actually works in this particular problem. So, I don't know. I like 0, 0. That's a good one. But what would a nice number be that I could multiply by 0.2 and end up being with something that's nice? Well, here's what I know. I know that 0.2 is like 1/5, right? I know that decimal conversion. So another number that I may try is 5, right? So 0.2 times the absolute value of 5. Let's see here. 0.2, the absolute value of 5 is 5 times 0.2. That gives me 1. Check it out in your calculator. You don't believe me. 10 is another nice number that will work. And 10 times 0.2 gives me 2. I'll go the other direction as well and come up with these other two values. Try it out in a calculator if you don't believe me. Go ahead. I'll pause the video, take a look. Make sure you know where I got those numbers. So it's here, 0, 0. And then look how nice it is. I can plot -5, 1 and -10, 2. That's nice. And then I can plot 5, 1 and 10, 2. Wow, okay. Well, there's a V. It's a very wide V. And I challenge you that if you would have used my original table of values, would you have gotten that same graph? I'm not so sure. So there's c of x, which is equal to 0.2 absolute value of x. And now let's graph the parent function in there. It just looks a little something like this. Okay, so what would I say? I would say c of x is wider than y equals the absolute value of x, or the parent function, right? Definitely wider. What happened here is I had a vertical shrink is what I had going on here. Okay. All right, hang in there. We got one more example, one more type of problem to take a look at. And I'm gonna tell you this, these are not as bad as it's gonna look. So we're gonna use a graphing calculator. Do you see that? A graphing calculator. This could also mean we use Desmos, right? That's a great website that we've used in the past that might be helpful here. So we're going to use a graphing calculator or a graphing utility to graph g of x and its parent function and then describe the transformations. So what I've done is I've went out to Desmos and I've actually graphed this function. It looks like this right here. So when I type it in and I look at Desmos, I get the red graph down here. So that's what you're looking at. You're looking at this red graph being g of x, the original function that I have. I want to compare that to the parent function. Okay, the parent function. What's the parent function? Well, I should see absolute value. So that's absolute value, and I should be seeing that. I should be seeing absolute value. So I will graph the absolute value parent function. Right? We'll put that up here, and we'll graph that. Right there it is. The green line is, in fact, y equals the absolute value of x. So now let's talk about how did we go from the green line to the red line? Well, one of the things I noticed that my V is in fact pointing down instead of pointing up. What does that mean? That means that the first transformation that happened was a reflection, right? We took that graph, we reflected it, which would make it point down, but still look like a V, but like point it down. So that would be the reflection part that I would see. What happened next? Well, if I'm looking at it, let's see here. The tip of my V would still be at 0, 0. So the question is, how in the world did I get to this other graph? Well, if I look at it, it looks like I went over. It looks like I went to the left, right? I went left 5 units. So that's actually the second transformation. I went left 5 units. We'd call that a horizontal shift, left 5 units. And then the last thing. What's the last thing that happened? Well, if I look at it, it looks like I did, in fact, go down. How many units? Well, it looks like 3 units. So it looks like I went down 3. Now, you got to be careful, right? Down 3. Don't count lines. count units. Notice what I'm counting by. I'm counting by 0.5s. Every one of them little tiny lines is 0.5. So don't be confused by that, right? There's 1, there's 2, there's 3 that gets me there. It was the same thing when I moved to the left 5 units. So this is what we should be looking for when we're comparing the parent function, which is the green curve, to g of x, which is the transformed curve. Okay. So try these two out. Again, you're going to use that graphing utility. That Desmos is going to be perfect here for you. So use that, graph the original function, the parent function, and then the g of x function for number 8 and the d of x function for number 9. Give those a try. See if you can list all of the transformations. We'll go over those here in a second. So pause the video now, try them out, and then come back. Okay, here it is. Here's the g of x function, right? The g of x function is graphed here in red. You'll see that this is g of x. Let's compare that to the parent function. Well, let's see here. That is linear for sure. So let's compare it to the linear function, which is going to look like what I've drawn up here on the screen. Ooh, that's bad drawing. But you get the idea. What happened? Well, my yellow line, my parent function, which is y equals x, is pointing up. But my red function is clearly decreasing. It's going down. So what happened? Well, we had a reflection. What else happened? Well, let me look here. Let me see here. Definitely there's been a change in slope, right? It's definitely not up 1 over 1. I don't know what it is. It looks like, oh, it's negative 1/4, right? So we had a change in slope. And what else happened? Well, I was here, and it looks like I went up 5 units. So up 5 units. A reflection, a change in slope, and we moved up 5 units. Let's take a look at the last one. So here's d of x. This is 3 times the quantity of x minus 5 squared minus 1. Let's look at the parent function. So if I plot those points in here, which has me points at, sorry about that. Hold on a second. Okay, there we go. We are going to plot the parent function, which is going to be this blue curve right here. All right, so that is y equals x squared. And of course, the red curve is my d of x function. Now, it might be hard to see. Might not be hard to see. But do you see how d of x looks like it's narrower, right? So that's one of the things that has happened. I definitely got narrower with that curve. It's gotten thinner. What else happened? Well, let's see here. It moved to the right. We moved right. How many units? Let me count here. So we got 1, 2, 3, 4, 5. Looked like it moved right 5 units. And then what else? Well, it looks like it's moved down 1. So it got narrower, it moved right 5 units, and it moved down 1 unit. Folks, that's all I got for you today. So go ahead, let me know if you have any questions, and good luck on your homework.